As you sit in your living room today, a colossal heat engine deeper than Mount Everest and wider than entire continents is quietly spinning out of control. Right beneath the calm blue surface of the Pacific Ocean, invisible currents are storing an unimaginable amount of trapped thermal energy. Thousands of scientific sensors floating in the dark ocean waters are sending back emergency readings to laboratories on land. The numbers are climbing so fast that climate scientists around the world are staring at their computer monitors in complete disbelief. If you love exploring real planetary mysteries and scientific discoveries without any fake drama, take 2 seconds to hit that subscribe button right now. Joining our channel means you will always stay ahead of the curve with clear, honest science that explains how our changing world actually works. To truly understand why leading Earth scientists are issuing such urgent warnings today, we need to go back in time and look at how humans first began studying global weather. More than 100 years ago, weather forecasting was a very local and simple science. Scientists used basic mercury thermometers placed inside small wooden boxes situated a few feet off the ground. They checked these station thermometers every afternoon, recorded the high and low air temperatures in paper logbooks, and tried to predict what tomorrow would bring. For many decades, this traditional approach seemed to work well enough because human civilization existed mainly on dry land. People stepped outside their front doors, felt the warm air on their skin, and assumed that the air around them was the main place where thermal energy lived. Standard textbooks taught generations of school students that climate was simply a pattern of air temperature, rainfall, and wind speed. When summers felt hotter than usual, people naturally assumed that the atmosphere itself was holding all that extra warmth. However, that basic view of our planet turned out to be missing the biggest piece of the entire puzzle. In the late 20th century, marine researchers began to realize that the atmosphere is actually just a thin, delicate blanket wrapped around an ocean-dominated world. Air is light and diffuse, meaning it cannot hold very much thermal energy before its temperature rises significantly. Liquid water, on the other hand, is extremely heavy, dense, and chemically unique. In high school science classes, teachers often demonstrate how water absorbs heat using a simple glass beaker and a Bunsen burner. If you place a dry metal pan over a flame, the metal gets scorching hot in just a few seconds. But if you fill that same pan with cold water, it takes a long time for the water temperature to creep up even a single degree. That is because liquid water possesses a remarkable property called high specific heat capacity. Water molecules hold onto each other tightly, requiring vast amounts of incoming energy just to speed up their molecular motion. Because oceans cover more than 70% of Earth's surface and extend down several miles deep, they act as an enormous planetary heat sink. When sunlight hits the Earth, most of it strikes ocean water rather than dry land. For over a century, as factories, automobiles, and power plants released billions of tons of heat-trapping gases like carbon dioxide into the sky, those greenhouse gases created an invisible thermal blanket. But instead of all that trapped heat staying in the air we breathe, the global ocean stepped in and quietly absorbed the vast majority of it. Scientists now know that the world's oceans have absorbed more than 90% of all the extra heat trapped on Earth over the past 50 years. That leaves less than 10% of the extra thermal energy to warm up the atmosphere, heat up the land, and melt mountain glaciers combined. In simple terms, our oceans have been functioning like a giant planetary air conditioner, working overtime day and night to keep land temperatures cool enough for human communities to thrive. Think about what that 90% figure really means for our daily lives. Every record-breaking hot summer day you have ever experienced, every blistering heat wave, and every warm night was produced by only a small fraction of the total excess energy trapped on our planet. More than 9/10 of the giant thermal surge has been quietly hiding beneath the waves, far out of sight and out of mind for most people. To track this hidden underwater heat, international research agencies launched a revolutionary global monitoring network called the Argo program in the early 2000s. The Argo network consists of roughly 4,000 robotic floats distributed across every open ocean on Earth. These autonomous floats sink down to depths of 2,000 meters, which is over 6,000 feet below the surface, drifting along deep ocean currents for days at a time. As these robotic floats slowly rise back up to the surface, their built-in sensors take continuous, highly accurate measurements of water temperature and salinity. Once a float reaches the surface, it beams its collected data up to orbiting satellites, which immediately transmit the information to research centers in the United States, Europe, Asia, and Australia. For the first time in human history, scientists gained a real-time, three-dimensional view of the deep ocean's changing thermal structure. When oceanographers began analyzing the millions of data points coming back from the Argo floats, they discovered that the ocean is warming at a rate never seen before in human record-keeping. The deep ocean was not just slowly receiving heat from the surface, it was soaking up massive amounts of thermal energy deeper and faster than early computer models had ever predicted. To quantify this staggering amount of underwater heat, scientists use a specialized measurement unit known as the zettajoule. One single zettajoule is an incomprehensibly large number, represented by the number 1 followed by 21 zeros. To put that in perspective, 1 zettajoule of energy is roughly equal to 250 times the total amount of electricity produced by every power plant on Earth, combined in an entire year. Recent official data from international climate institutions shows that the upper ocean absorbed more than 15 to 20 zettajoules of extra heat in a single recent year alone. That amount of energy entering the ocean is equivalent to detonating several atomic bombs inside the water every single second of every day, all year long. All of that relentless power is stored inside seawater, steadily charging up the ocean battery. Did you know that thousands of robotic floats are currently drifting deep underwater right now to measure this hidden energy? Leave a quick comment below if you have ever heard of the Argo program before, and don't forget to give this video a like so more people can discover this fascinating science story. For a long time, mainstream climate scientists expected that ocean warming would remain a slow, steady, and predictable background process. The general scientific consensus 20 years ago was that the oceans were so vast and deep that it would take many centuries for surface water to get dangerously warm. Researchers assumed that cold, deep-sea currents would continuously mix with warm surface water, diluting the heat and keeping coastal air temperatures relatively stable for generations to come. However, what marine scientists actually observed over the last few years completely upended those old assumptions. Instead of warming slowly and evenly, the upper layers of the ocean began experiencing sudden, extreme spikes in surface temperature. Starting in 2023 and continuing into recent years, global sea surface temperatures shattered previous historical records by margins that shocked even the most experienced researchers. In key regions, like the North Atlantic Ocean and the equatorial Pacific, surface water temperatures rose several degrees above historical averages across millions of square miles. Ships traveling across these oceanic zones recorded warm water conditions normally found in tropical lagoons. The gap between what computer models had predicted for this decade and what thermometers were actually measuring in the water was the largest ever recorded. Why does this dramatic, unexpected leap in ocean temperature matter so much to someone living miles away on land? Because when the surface layer of the ocean becomes exceptionally hot, it loses its physical capacity to absorb more thermal energy from the atmosphere. Instead of pulling heat out of the air, the overheated ocean begins radiating its massive thermal storage directly back up into the lower atmosphere, turning the planetary air conditioner into a giant space heater. Scientists use a concept called Earth's energy imbalance to explain what is happening on a global scale. Under normal historical conditions, the amount of energy Earth received from sunlight was virtually identical to the amount of thermal energy Earth radiated back out into cold space. This balance kept our planet's global average temperature stable enough for human agriculture in cities to flourish over thousands of years. Today, however, satellite sensors operated by space agencies like NASA confirm that Earth is absorbing far more solar energy than it can radiate back into space. The trapped energy is accumulating at an alarming rate because high concentrations of greenhouse gases in the atmosphere act like an insulating glass dome. The total energy imbalance has nearly doubled over the past 20 years, meaning our planet is accumulating heat faster than at any other point in satellite history. The primary driver behind this growing insulation is the steady rise of carbon dioxide molecules in our atmosphere. Recent background air sampling from high-altitude observatories like Mauna Loa shows carbon dioxide concentrations pushing past 423 parts per million. Geologic studies of ancient ice cores and ocean sediments show that atmospheric carbon dioxide has not reached this level on Earth for over 3 million years. Back during that ancient epoch, known as the Pliocene, global sea levels were roughly 50 to 60 feet higher than they are today, and large trees grew near the North Pole. The main reason our current surface air temperatures have not yet matched those ancient conditions is simply the delay caused by the ocean's vast thermal inertia. The ocean has been buffering us from the full impact of greenhouse gases, but that buffering phase is rapidly drawing to a close. As the top layers of the ocean continue to absorb thermal energy, water molecules physically expand and take up more space. This natural process, called thermal expansion, accounts for about half of all global sea level rise observed today. Combined with hundreds of billions of tons of fresh water pouring into the ocean each year from melting glaciers in Greenland and Antarctica, rising sea levels are threatening coastal communities around the world. Glaciologists using high-precision radar equipment have found that major ice sheets are melting from both above and below. Warm atmospheric air melts the surface of the ice during summer months, creating deep blue meltwater lakes that carve shafts down through the glaciers. At the same time, warm ocean currents are creeping beneath floating ice shelves, eroding the structural foundations of giant glaciers from below and speeding up their slide into the sea. What researchers discovered next in atmospheric wind patterns revealed an even more direct connection between ocean heat and extreme land weather. They found that as the ocean releases its stored heat into the air above, it fundamentally alters the high-altitude jet streams that control daily weather movements across entire continents. Have you noticed that severe summer weather seems to park over the exact same regions for weeks on end nowadays? Tell us what the weather has been like in your part of the world down in the comments, and subscribe to stay updated on how planetary systems affect our everyday lives. To understand how ocean heat alters land weather, we need to look at how global atmospheric winds work. High in the atmosphere, fast-moving rivers of air called jet streams rush around the northern and southern hemispheres from west to east. These jet streams are generated by the sharp temperature contrast between the freezing polar regions and the warm tropical regions near the equator. When the temperature difference between the poles and the equator is large, the jet stream blows strong, fast, and relatively straight. However, because the Arctic region is heating up more than twice as fast as the rest of the planet, the temperature gap between the pole and the equator is shrinking rapidly. As that temperature difference grows smaller, the jet stream loses its forward momentum and begins to slow down. Instead of flowing in a smooth, straight path, the weakened jet stream starts to bend into giant sluggish meanders that loop far north and south across continents. Meteorologists refer to these large, slow-moving atmospheric loops as persistent weather patterns or atmospheric blocking events. When a giant loop of the jet stream gets stuck over a specific continent, it locks weather systems in place for weeks at a time. A rainstorm can sit over one region until massive flooding occurs, while a high-pressure system can park over another region, baking it in continuous sunshine day after day. These stuck high-pressure systems are commonly known as heat domes. Inside a heat dome, sinking air compresses and warms up significantly, creating an invisible lid that prevents hot air from rising and escaping. At the same time, clear skies allow relentless solar radiation to beat down on the ground, evaporating every last drop of moisture from plants and topsoil. Under historical weather patterns, a summer heat wave would typically last 2 or 3 days before a fresh weather front pushed it away. But under a slow, wavy jet stream, a single heat dome can remain stationary over the exact same states or provinces for 3 to 4 weeks straight. The soil becomes so dry that it can no longer absorb heat through water evaporation, causing all incoming solar energy to directly superheat the surrounding air instead. This dangerous cycle is known to atmospheric scientists as land-atmosphere feedback. Hotter air dries out the soil faster, and dry soil makes the air above it even hotter. By the time the atmospheric block finally breaks, local crops are scorched, water reservoirs are severely depleted, and electrical grids face historic demands as millions of homes run air conditioning systems simultaneously. Before we examine the biological limits of human heat endurance, there's another key detail that explains why simple room thermometers do not tell the full story. Standard weather forecasts usually report dry bulb air temperature, which measures how hot the dry air is. But dry air temperature alone does not capture how human bodies actually feel or survive in extreme conditions. To measure true heat risk on living organisms, medical scientists use a combined measurement called the wet bulb temperature. A wet bulb reading is taken by placing a thermometer wrapped in a water-soaked cloth into the open air. If the surrounding air is dry, water evaporates off the wet cloth rapidly, cooling the thermometer down significantly. This evaporative cooling process is identical to how sweat evaporates off human skin to lower internal body temperature. Human beings are remarkably good at regulating internal body heat in warm climates, provided the air is dry enough. When internal core body temperature rises, sweat glands produce liquid moisture on the skin. As that sweat evaporates into the air, it carries excess heat away from the bloodstream, keeping internal organs at a safe working temperature of around 98.6 degrees Fahrenheit. However, there is a strict physical limit to how much sweat can evaporate, and that limit is determined entirely by atmospheric humidity. If the air surrounding a human body is already saturated with moisture, sweat cannot evaporate into the air at all. It simply drips off the skin without providing any cooling effect whatsoever. For many years, physiological researchers considered a wet bulb temperature of 35 degrees Celsius, which equals 95 degrees Fahrenheit at 100% humidity, to be the absolute upper limit for human survival. Above that threshold, even a healthy person sitting quietly in total shade with unlimited drinking water and a fan cannot cool their body down. Internal core body temperature begins rising steadily toward dangerous, life-threatening heat stroke levels. What medical scientists recently discovered in clinical human trial chambers surprised the entire scientific community. Researchers at Pennsylvania State University placed healthy young adults inside specialized environmental chambers to test real-world human heat tolerance at various humidity levels. The empirical data showed that human heat stress actually begins at wet bulb temperatures much lower than 35 degrees. The university studies revealed that dangerous cardiovascular strain and internal body warming begin at wet bulb temperatures around 31 degrees Celsius, which is roughly 88 degrees Fahrenheit at high humidity. That means millions of people living in humid coastal regions could face serious biological risk at air temperatures that were previously considered survivable, especially as warm oceans pump vast amounts of water vapor into the lower atmosphere. Does high humidity make hot weather feel significantly worse where you live? Leave a comment sharing how you cope with uncomfortable summer heat, and be sure to hit that like button to help spread important health science awareness. To understand why climatologists warn that the most extreme global heat surges are still ahead of us, we must look at a massive natural ocean engine called the El Niño Southern Oscillation Cycle. Across the vast tropical expanse of the Pacific Ocean, trade winds and ocean currents periodically shift back and forth between two major climate phases known as El Niño and La Niña. During a La Niña phase, strong trade winds blow vigorously from east to west across the tropical Pacific. These powerful winds push warm surface waters westward toward Indonesia and Australia, while pulling cold, nutrient-dense water up from the deep ocean along the coast of South America. This upwelling of cold ocean water acts like a temporary global cooling break, keeping average global surface air temperatures slightly lower, even as total planetary heat continues to accumulate. Throughout certain recent years, weak La Niña conditions helped suppress global air temperatures, preventing them from reaching even higher peaks. But atmospheric scientists emphasize a critical fact. Even during cool La Niña phases today, global average air temperatures remain higher than during the strongest El Niño phases recorded 50 years ago. The baseline warming trend is now so elevated that even planetary cooling cycles are warmer than historical warm cycles. When the natural Pacific cycle inevitably flips from La Niña into a strong El Niño phase, the trade winds weaken dramatically or even reverse direction entirely. Without strong winds pushing warm surface water westward, the massive reservoir of heat stored in the tropical ocean sloshes back eastward toward the Americas. The temporary cold water lid disappears, releasing immense quantities of ocean thermal energy directly into the lower atmosphere. When a major El Niño combines with the record-high background ocean heat content we are seeing today, global air temperatures do not merely rise by small increments, they experience sudden, dramatic upward leaps. Climate monitoring agencies like the Copernicus Climate Change Service warn that the next major El Niño event could push global surface air temperatures into territory completely unprecedented in human history. Here is the underlying detail that climate researchers are analyzing with intense focus today. Over the past 15 to 20 years, the overall rate of global warming has shown clear mathematical signs of acceleration. On long-term climate graphs, the temperature line is not just climbing steadily upward. It is curving upward at a steeper angle than in previous decades. The warmest individual years ever recorded in human history have almost all occurred within the last decade. When climate scientists compare current real-world observations with older computer projections, they see that actual warming is tracking near the upper edge of historical forecasts. This acceleration is being driven by several powerful feedback mechanisms working at the same time: rising greenhouse gas concentrations, ocean heat saturation, loss of polar ice reflection, and changes in atmospheric aerosol pollution. For over a century, heavy industrial burning of coal and fuel oil released large amounts of sulfur dioxide gas into the sky. In the atmosphere, sulfur dioxide reacts to form tiny microscopic particles called sulfate aerosols. These microscopic particles act like a subtle reflective mirror in the upper air, reflecting a small percentage of incoming sunlight back out into space before it can hit the ground and turn into heat. However, as nations around the world passed clean air regulations to improve human health and reduce air pollution, sulfur emissions dropped significantly over recent decades. While cleaner air has saved millions of human lives from respiratory disease, it also removed a portion of that temporary aerosol sunshield. With clearer skies, more direct solar radiation strikes the ocean surface, unmasking the full heating potential of trapped greenhouse gases. Did you know that reducing industrial smoke pollution unintentionally revealed more of Earth's true underlying greenhouse warming? Share your thoughts on this complex scientific reality in the comments below, and subscribe so you never miss our in-depth science explanations. At this very moment, scientists are monitoring ocean heat measurements across every ocean basin on Earth. Data compiled by global oceanographic institutes shows that total heat content in the upper 2,000 meters of ocean water has broken world records for several consecutive years. In many marine regions, sea surface temperatures have reached levels never documented since modern satellite tracking began in the late 20th century. These elevated sea surface temperatures are not merely abstract statistics in a scientific journal. They are triggering severe real-world impacts across marine ecosystems. Coral reefs in the Pacific, Atlantic, and Indian Oceans are currently suffering from widespread, severe marine heat waves. When water temperatures stay too warm for too long, corals undergo a stress response where they expel the microscopic algae living inside their tissues, turning completely white in a process known as coral bleaching. If water temperatures do not cool down quickly enough, bleached corals starve and die, leaving behind barren limestone structures. While coral reefs cover less than 1% of the ocean floor, they provide critical habitat, nursery grounds, and shelter for more than 25% of all known marine species. The destruction of reef ecosystems threatens coastal fisheries that feed hundreds of millions of people around the globe. Superheated ocean waters also provide immense fuel for tropical storms, hurricanes, and typhoons. Tropical cyclones derive their energy directly from warm ocean water evaporating into the lower atmosphere. When sea surface temperatures rise well above 26 degrees Celsius, evaporation speeds up dramatically, feeding immense amounts of moisture and heat into developing storm systems. As a direct result, meteorologists are witnessing an increase in rapid storm intensification events. Rapid intensification occurs when a standard tropical storm suddenly transforms into a destructive Category 4 or 5 hurricane in less than 24 hours. These supercharged storms carry vast amounts of moisture inland, producing historic rainfall totals and severe flooding far away from coastlines. At the same time, regions far removed from ocean moisture are experiencing rapid onset agricultural droughts, often called flash droughts. Unlike traditional slow-moving droughts that take months or years to develop, a flash drought can occur in just a few weeks when high air temperatures and strong winds draw every bit of moisture out of topsoil and vegetation. This simultaneous emergence of intense downpours in some areas and severe flash droughts in others is a direct signature of a warming planetary system. Basic thermodynamic physics dictates that for every 1 degree Celsius increase in atmospheric temperature, the air can hold approximately 7% more water vapor. That means when weather systems release rain, downpours are much heavier. But when weather systems are dry, the thirsty air pulls moisture out of the ground with far greater force. The agricultural consequences of these rapid environmental shifts are profound. Global food production relies on stable, predictable seasonal weather patterns that farmers have relied on for thousands of years. When spring planting seasons bring unprecedented flooding, and summer growing seasons bring weeks of unbroken heat, crop yields for major staples like wheat, corn, rice, and soybeans can suffer major losses. What makes this issue so urgent right now is that human infrastructure was engineered for a historical climate that no longer exists. Our concrete highways, railway networks, power distribution lines, water pipelines, and residential buildings were designed based on 20th century temperature ranges. They were simply not built to withstand extended heat waves, where temperatures remain well above normal operational limits for weeks at a time. When extreme heat domes settle over major metropolitan areas, high voltage power lines expand and sag, train tracks buckle under thermal pressure, and asphalt roads can soften and crack. At the exact moment when cities require maximum electrical power to keep cooling systems running and protect public safety, electrical grids become less efficient because hot metal transmission lines experience higher resistance to electricity flow. To address these growing challenges, scientific teams and engineering groups worldwide are working to develop better early warning systems and resilient infrastructure. Climate researchers are using advanced satellite data and machine learning models to predict ocean heat movements and heat dome formations weeks in advance, giving communities crucial time to prepare. Understanding these complex planetary mechanisms is essential for navigating the future with wisdom and clarity. The thermal energy accumulating in our ocean depths represents a massive physical force that will continue shaping weather patterns, food production, and coastal geography for generations to come. By examining clear scientific data without panic or denial, human society can make informed, practical decisions about energy, infrastructure, and environmental stewardship. If you enjoyed this comprehensive breakdown and want to keep learning about real science stories shaping our planet, please take a second to hit the subscribe button, turn on all notifications, and drop a like on this video. Leave a comment below answering this question. What is one practical change you think your local community should make to prepare for extreme weather? Thank you so much for watching, and we look forward to seeing you in the next video.